Hello again. In this video, we're going to look at higher order derivatives. And so to introduce this idea of a higher order derivative, let's just look at an example. Okay, suppose you have some function f of x equal x to the fourth power. Okay, and let's say you want to find the first derivative of this function. Well, you could find the first derivative of this function using the power rule, and it would simply be 4x cubed. Remember, the 4 gets multiplied by this in front, and then you subtract 1 from the exponent. Okay, so using the power rule, that would be the derivative of this function. And of course, we denote that by putting a prime next to the f. But since this is a function unto itself, I can actually find the derivative of this function. And of course, if I were to find the derivative of this function, I could do that using the power rule. The 3 would come down in front and get multiplied by the 4 to give me 12, and then I would subtract 1 from the exponent, and that would leave me with x squared. But since this is the derivative of f prime, we're going to call this the second derivative of the original function f of x. And we denote that by putting 2 primes next to f. Okay, so this is called the second derivative of f of x. And then there's no end to this. I could take the derivative of this function, and that's known as the third derivative of the original function. And you can denote that by putting 3 primes next to f. And again, using the power rule, you would get 24x here. Okay. Now you can continue to put primes here, but also at some point you may want to start using just a number. And so if I take the fourth derivative, you can use a 4 to denote 4 primes. So this would stand for the fourth derivative of the original function. And that's simply the derivative of the third derivative. Okay, and so the derivative of this would just be 24. Okay, so there's no end to this. You can take the fifth derivative, the sixth derivative, the seventh derivative of this original function. And these are called higher order derivatives. Okay, and one way of notating these higher order derivatives is to continue to put primes next to f, or put a number in parentheses next to f to denote the order of the derivative. But you can also use Leibniz's notation to notate this derivative, or higher order derivatives. So let's say you have some function and you take the derivative of it. Okay, so in Leibniz's notation, you would write it like this. Now remember, this is called the derivative operator, and it's operating on this function. And so it just means take the derivative of f with respect to x. Of course, you could also write it like this. Okay, but let's say you wanted to find the derivative of this function. Okay, well then you would just say this derivative operator is now operating on this function. Okay, and that's how you would denote it. Of course, another way of denoting it is, since we have two d's here, sometimes we write this as d squared, and then we have two dx's here, and we denote that with dx squared. And this is called the second derivative operator, and in this case it's operating on f. Okay, so I want you to be careful about this. Notice the f doesn't have a square on it. Only the d has a square on it, and the dx has a square on it. Now the dx is one symbol unto itself. And so when we say dx squared, we mean dx and another dx. Now a lot of times when we have variables that we're multiplying together, if I have like x times y, we denote that as x times y squared. But this is not multiplication, so I don't want you to misinterpret this. This is not d times x squared. You can't, that's not what, in this context, that's not what this means. Okay? This is dx, which is one symbol unto itself, And then when we're putting this square here, we're just meaning there's two dx's next to each other. Notice that's different than when you're working with these algebraic operations of multiplication. When I write this, it means x times y times y. Okay? So just be careful about this. When you write dx squared, this does not mean d times x times x. That's not what this means. Okay? So if you see the second derivative operator operating on a function, what it means is you're taking the derivative of the function, the first derivative of the function, and then after that you're taking the derivative of that again, of that new function. Okay, so this is how we denote higher order derivatives using Leibniz's notation. Okay, and you just continue to do this. The third derivative operator would look like this. And of course, it means you're going to take the derivative of this function 3 times in succession. Okay, so we have two notations for higher order derivatives. We have Leibniz's notation and we have our prime notation. Okay, so let's just do a couple more examples. Let's say you want to find the third derivative of this function. Okay, so in order to do that, you would just have to continue to take the derivative of this function until you get to the third one. Okay, so the first derivative would be 9x squared minus 5x plus 0, using the power rule. And then the second derivative would be the derivative of this function. Again, using the power rule would just be 18x minus 5. And then the third derivative would be the derivative of this function, which is just 18. Okay, and let's do the same thing for part B. Let's find the third derivative of this function. Now in this case, you can denote this by using prime notation. This time you would just put a prime next to the y, since y is the output variable here instead of f. Okay, and the assumption here is we're taking this derivative with respect to t, since the independent variable is t here. Up here, we're taking the derivative with respect to x, since the independent variable is x. Okay, so we're going to find the third derivative of this function with respect to t. In fact, I'm going to use Leibniz's notation just to be different. Okay, so the first derivative of y with respect to t would be the derivative of, this is equal to y, right, would be the derivative of this 2t plus 3 times e to the t. Okay, so let's find out what that is. So this is just equal to 2. In fact, let me break this up into, you can break it up across addition, right? So you can find the derivative of this first piece and add it to the derivative of the second one. But the derivative of this is simply 2, right? Okay, and then the derivative of this, you can pull the 3 out. So you can pull constants outside the derivative operator. So let's pull that 3 out. And then the derivative of e to the t with respect to t is just e to the t. And we saw that in a previous video. You may remember the derivative of e to the x is simply e to the x. Okay, which means the derivative of e to the t with respect to t is still e to the t. Okay, so this is our first derivative of y with respect to t. Now let's take the derivative of that. And that'll give us the second derivative of this function with respect to t. Okay, again, you can break this up across addition and find the derivative of each of these individually and then add them up. And then notice you can pull this 3 out front again since it's a constant. So it can come outside the derivative operator. And it looks like you're left with the derivative of 2 is 0. And then the derivative of e to the t with respect to t is e to the t. And so you just get 3e to the t. Okay, and so that's our second derivative of y with respect to with respect to t. Okay, and so we have to do this one more time to find the third derivative. And I'm going to write it like this now. So the third derivative. So this is how we denote the third derivative operator. So the third derivative of y with respect to t would simply be the derivative of this second derivative. Okay, with respect to t. And again, you can pull the 3 out front since it's a constant, and then you're taking the derivative of e to the t with respect to t, and you just get e to the t. And so you end up with 3 times e to the t. And so that's the third derivative of this function, right, with respect to time, or t. I'm assuming t stands for time, but with respect to t. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.